Thanks to Brilliant for sponsoring today's video.
I want to talk about a very little bit of classical algebraic geometry. And maybe before we get started, I'd like to just mention that I've got several graduate algebraic geometry textbooks, and every once in a while I'm like, well, today I'm going to start learning algebraic geometry. But I find it such a difficult subject. The way that it's done kind of in the modern sense, which is so abstract, that's kind of neither here nor there. Like, for instance, I can't wrap my head around what a sheaf is. Okay, but anyway, that's not what we're talking about here. We're talking about very classical, very simple algebraic geometry. And in particular, we want to look at the most general type of quadratic curve, and then look at what that curve might represent if we were to look at its graph. So the most general quadratic curve would be of the following form. So we have ax squared plus bxy plus cy squared. So those would be all of the degree 2 parts. And then plus rx plus sy. So those are all the degree 1 parts. And then plus t equals 0. That's obviously a constant. And I just point out here that a, b, c, r, s, t are all real numbers. But they're really just real numbers for now. We're going to expand this near the end of the video. Now, I'm going to present this fact without any proof, although we will motivate it, and that is, outside of degenerate cases, all curves of this form are either ellipses, hyperbolas, or parabolas. So what do I mean by degenerate cases? Well, let's observe that if a, b, and c are equal to 0, then in fact you would simply have an equation of a line. So that would be an example of a degenerate case. And furthermore, you could maybe envision some sort of situation where this left-hand side factors into a perfect square binomial, or maybe just like a product of two linear polynomials in x and y. And then, well, what we would have is an expression which defines two lines, and that would be another degenerate case. So those aren't the ones that we're looking at. Okay, so what I'd like to start with is to prove that, well, in fact, not only are these curves just ellipses, hyperbolas, or parabolas, they're in fact all maybe equivalent in a sense to the nicest ellipse, the aka the unit circle, the nicest hyperbola, the unit hyperbola, and maybe the nicest parabola y equals x squared via some sort of transformation. So let's start with a very basic example, and then we'll see how this goes a little bit more generally. So let's start with the following equation of an ellipse. So we have x minus h squared over a squared plus y minus k squared over b squared equals 1. So what is the graph of this? Well, it's going to be an ellipse. So let's maybe get an ellipse drawn on the board. And then, well, we can label some points on this ellipse. So this point way out here corresponds to, well, this bit collapsing because it's on the major axis. So this would be of the form, let's see, h plus a comma k. And then this over here, which is also on the major axis, would be h, or a minus a, no, h minus a comma k. And then up here on the minor axes, we have h, and then we have k plus b, and then here we have h and k minus b. Okay, so there's our maybe like very simple ellipse that isn't a circle. Now let's make a transformation of this. And what sort of transformation do we want to make? Well, let's perhaps set capital X equal to x minus h over a. And then we'll set capital Y equal to y minus k over b. So, well, that has the effect of, well, shifting this plane around, as well as perhaps we're like constricting it or we're expanding it. Okay, so that's going to give me a new set of equations, but I think it's pretty easy to see that the new set of equations is capital X squared plus capital Y squared equals 1. So what we have here is, well, it's simply the unit circle. Okay, so I think this motivates maybe the nicest ellipse being able to be, transformed into the unit circle. Let's maybe look in parallel at what's happening with the nicest hyperbola, or, transforming into a nice hyperbola. So let's say we have x minus h over a squared. I'll go ahead and factor the square out, and then minus y minus k over b squared equals 1. Okay, so, well, like I said, that's going to be a hyperbola. It is opening to the left and the right. And then we can look at these 2 points here. I don't really know what the names of these points are. Maybe you can post in the comments if you know the names of those points. So let's see, this coordinate right here would be h plus a comma k. And then this point right here is h minus a comma k. And now, well, we can do the same change of variables, but instead of doing that same change of variables, let's do a slightly different change of variables just to show that we can transform this maybe more than we're just thinking about originally. Let's set y equal to x minus h over a, and we'll set capital X equal to y minus k over b. And that's going to give us equations y squared minus x squared equals 1, which is now the hyperbola opening up and down instead of left and right. So we had like a suitable transformation of, well, this nice hyperbola here to the other hyperbola. Okay. So, well, what happened there? Well, the effect that happened there was, well, we collapsed the plane a little bit, and then maybe we rotated it and shifted some things as well. And you could imagine like a very nice parabola could be shifted and stretched into place where it's the parabola y equals x squared as well. So let's see more generally how this thing might happen.
I'd like to take a minute to talk about today's sponsor, Brilliant.org. While watching my videos is a great place to start, you get more out of learning by doing. And that's why I highly recommend you sharpen your skills with Brilliant. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI that are individually matched to your unique level. Each lesson comes with hands on problem solving so you can truly learn the material. It's been proven to help you learn 6 times more effectively than just watching videos. Courses are designed by an award winning team from MIT, Duke, Caltech, Microsoft, Google, and more. You will find yourself learning real life problem solving skills instead of memorizing equations. Brilliant can also be easily incorporated into your daily activities, with fun lessons you can do on your phone, tablet, or computer in just minutes a day. Check out their new course library. They have lessons on large language models. You can learn hands on with real language models. They can even show you the importance of training data by comparing models trained on Taylor Swift lyrics to models trained on a cookbook. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/michaelpenn for a 30-day free trial and 20% off your annual subscription. Thanks once again to Brilliant for sponsoring today's video.
So all of those examples that we just looked at are really just very, very special cases of, a so-called affine transformation. So an affine transformation will change from variables little x, little y to variables capital X, capital Y in the following way. So this vector, capital X, capital Y, will be equal to this matrix ABCD times the vector little x, little y plus a constant vector, which I've called RS here. And I'd like to point out here that AD minus BC cannot be 0. That's the determinant of this 2 by 2 matrix. And that's because, well, we want this matrix to be invertible because if it's invertible, then this transformation is reversible and it's like not information destroying, if you will. Okay, so let's do an example. So let's take the unit circle, the unit hyperbola, and maybe the simplest parabola. I would call it the unit parabola, but in another video that is gone up on the channel recently, or may come up on the channel in the future, I'm not really sure of the release date, I called the unit parabola something else. Okay, so anyway, we want to transform these three very, very nice quadratic curves into things that aren't so nice. So let's say we have the following transformation. So we've got vector capital X capital Y is 3, 1, 4, 2 times little x little y plus vector -1, 2. Okay, so now multiplying this out shouldn't be too bad. So capital X will be 3x plus y, and then let's see, -1. That's just by doing standard matrix vector multiplication. And then here we have capital Y will be 4x plus 2y plus 2. So I think immediately you can see how this transformation is a little bit different or more general than the type of transformation that we saw before, in that we're mixing the variables little x and little y into variables capital X, capital Y. Okay, so let's see. If we've got capital X squared plus capital Y squared equals 1 here, that's going to give rise to the following new, well, it's going to be an ellipse. And I guess I'm not proving here that an affine transformation always takes ellipse to ellipse, hyperbola to hyperbola, and parabola to parabola. That's actually not super difficult. It just involves a lot of like messy calculation. But I guess what we should say is that these types of quadratic curves are invariant under affine transformation. That means in ellipse class, affine transformation just loops back to ellipse class. Hyperbola class will loop back to hyperbola class, and parabola class will loop back to itself as well. There's no affine transformation that will turn an ellipse into hyperbola, for instance. Okay, so anyway, if we do this transformation here, so what you'll get is 25x squared plus 22xy, and then next will be plus 5y squared, and then plus 10x plus 6y equals -4. So this equation over here represents an ellipse, and I'll put a graph of that ellipse on the board right now, or on the screen right now. And now, well, we could do the same kind of thing. We could transform the unit hyperbola, x squared minus y squared, via this affine transformation, and we'll get a new unit, or we'll get a new hyperbola, and it'll be of this form. So we'll have 7x squared plus 10xy plus 3y squared plus 22x plus 10y equals 2. And I'll put a graph of that hyperbola on the board as well. And then, well, we could take the simplest parabola, y equals x squared, and do a transformation as well. And that'll give you the following. So we'll have 3y equals 9x squared plus 6xy plus y squared minus 6x plus 1. And I'll put a graph of that hyperbola on the, and I'll put a graph of that parabola on the screen right now. And then maybe for good measure, let's put all of these graphs on the same set of axes. And one thing that you might notice here is that the shifted and stretched, or I should say transformed, unit circle and unit hyperbola have this nice kind of tangent property that's inherited from the original, tangency property of the original curves. Okay, so I guess maybe the next question, or what I think is the next obvious question is, well, if we had not known that this guy over here, this 25x squared plus all the stuff, arised from a transformation of the unit circle, or this 7x squared plus stuff arised from a transformation of the unit hyperbola, and so on and so forth, how would we know that these equations over here represented, well, an ellipse, a hyperbola, and a parabola? And well, we won't go through the details of maybe making a theorem and proving it, but I will present that result right now. So here's that result. So assuming that this curve up here is not degenerate, so in other words, it doesn't collapse to a line or maybe a collection of lines, then if b squared minus 4ac is 0, this thing is a parabola, where let's recall that b, a, and c were the coefficients of the quadratic terms. If b squared minus 4ac is less than 0, it's an ellipse. And if b squared minus 4ac is bigger than 0, it's a hyperbola. Okay, so now before we finish up, I'd like to maybe do a little bit more. And that is, let's extend our view to curves in, well, the two-dimensional complex space, which is four-dimensional real space. So maybe we could rewrite the curves here as az squared plus bzw plus cw squared plus rz plus sw plus t equals 0. So that's our curve now. You know, curve is kind of stretching the imagination because it actually has more than one real dimension, although it has one complex dimension for what that's worth. And here, z and w are our complex variables, and a, b, c, and d, and I guess r, s, and t. Oh, and there's actually no d here. So a, b, c, r, s, and t are all complex constants. And now, well, I'd like to point out that in this case, and we can see this very, very easily. In fact, there's almost no work for this next step after, we assume all of the stuff is true over the real numbers. And that is here, ellipses and hyperbolas are the same. So ellipses equal hyperbolas. And you might say, well, that's crazy because ellipses form this closed shape, whereas hyperbolas explode out in two directions. But you're thinking only in the real plane there and not the complex plane. And I claim that we can see this by only looking at the unit circle. And that's because, well, by what we saw over here with affine transformations, any ellipse can be transformed to the unit circle, and then any hyperbola can be transformed to the unit ellipse. So if we show that the unit circle and the unit ellipse can be transformed into one another, or they're in fact two sides of the same coin, then, well, any ellipse can be transformed into any hyperbola. But let's do it like this first. So here, I claim that this z squared plus w squared equals 1. That's the unit circle in, well, I would say the complex plane, but complex 2 space. Okay, but now what I want to do is look at the level curves of this in a couple of slices. So let's write over here that we have z is equal to x plus iy, and we'll write w is equal to u plus iv. So x and y are the real and imaginary parts of z, and u and v are the real and imaginary parts of w. So if we take this curve, which is not really visualizable because it lives in c cross c, which is four-dimensional real space, and we look at the slice on the x-axis and the u-axis, well, so that'll be the slice when y and v are equal to 0. But if y and v are equal to 0, then this equation right here collapses to x squared plus u squared equals 1. And so, well, that is just the unit circle as, we know and love. Okay, great. So, well, one slice of this is the unit circle. So I guess that's good news. But now let's do another slice of this. Let's maybe do the slice where we take the real part of z and the imaginary part of w. So in other words, we're slicing when y is equal to 0 and u is equal to 0. So that's going to give us x squared minus v squared equals 1. Then if we draw this with the x-axis here and the v-axis here, then that's our unit hyperbola opening to the left and the right. So there we have it. Inside of this unit circle, there's a unit circle. I guess I should say inside of this complex unit circle, there's a real unit circle and there's a real unit hyperbola opening to the side. But in fact, if we make a slice with the other choice of real and imaginary axis, maybe the case where we take the imaginary part of z and the real part of w, so that would be u squared minus y squared equals 1. That's in fact going to give us a hyperbola opening the other way. So let's see, how do we want to do this? Maybe we'll say this is y and this is the u-axis. So there we've got a unit hyperbola opening this way and this way. And then, well, what do we get if we take the imaginary part of both? Well, I'll just talk through this. So that would give us iy squared plus iv squared. So that's like minus y squared minus v squared equals 1. But since v and y are both real, there are no solutions to that. So that's kind of a blank. Okay, so there we have it. Inside of the unit circle, we have... So there we have it. Inside of the complex unit circle, we have a real unit circle and then the two, real unit hyperbolas. And then, well, now that we're allowed to use complex numbers, there's a very, very simple transformation that will transform, well, this equation, which is our complex unit circle, to a complex unit hyperbola. And that would be something like this. Let's take capital Z and set it equal to little z, and we'll take capital W and set it equal to I times little w. So that's obviously going to give us capital Z squared minus capital W squared equals 1. So now if you really want to go at it, well, what you can do is you can start with a unit hyperbola, or any hyperbola I should say, transform it into this hyperbola, do this transformation in reverse, and then transform it to any ellipse you want. So that's like kind of the path towards, well, this fact right here, which was the whole point of the end, and that is in the complex 2 space, ellipses are hyperbolas. But actually that's not all. If we expand our world even bigger, parabolas are also in the same class as ellipses and hyperbolas. But we're not going to do that today. Maybe post in the comments if you'd like to see that. And that's a good place to stop.